Students, the next topic we're going to see is closed sets. Already we discussed what are open sets. Now we're going to discuss what are called closed sets in metric spaces. The topic name is closed sets. And the properties and theorems related to closed sets. First, we are going to see what is a limit point of a set in a metric space. So the definition: what is a limit point of a metric space? That is the first definition we are going to see before defining what is a closed set. This is a topic. The topic is closed set, and the first definition is what is called as limit point of a set in a metric space. In general, we call it as a metric space. Now, the definition is, let's suppose E be any subset of a metric space, say M. It is suppose M is a metric space with a metric row, and something like this. E is a subset, and now let the point say X in M, not necessarily in E. It may be here or it may be sometimes here. Anything is possible. Suppose X in M. A point X in M is called a limit point. Is called a limit point of the set E if there is a sequence, of points, because we have to use the word points instead of real numbers, we have to use the word sequence of points, say Sn, sequence of points of the set E which converges to this X. And if this is the case, when we say a point X is called as a limit point of the set E, the meaning is there must be one sequence inside E that is converging to this X. And now we collect all those limit points of the set E. Now, for a set there will be many limit points, and now we collect all the limit points and put it like a set, and that set is called as the closure of the set. Closure of the set E. That is a next definition, but you can make a note of that. The set be denoted by the symbol E bar. In the set E, you put a bar overlaps. Set E of all limit points. Set E of all limit points of the set E is called the closure of the set E. Suppose this is a metric space M, and suppose this is a set E. Suppose X is a limit point, if we say. So what's the meaning is there exists a sequence of points in E that is converging to X. Suppose Y is also a limit point. There exists some other sequence that is converging to this Y. So, but it won't be very far away like this. Something like this. This is X and will be Y. We may ask a question whether this X and Y, the limit points will be inside this E or it will be outside it. Both are possible. We are going to see all the different definitions. What happens if now you collect all the limit points of the set X, Y of the set E. all the limit points we collected, and all the limit points we collected, and that set we call it as closure of the set E. That is a definition. Don't want to visualize it. All the limit points you put it as a set. And that set we call it as what? This is the symbol we use. Closure of the set. Denoted by E bar. Like this. That is, it contains all the limit points of the set E. Now the question is, E bar is a set and E is another set. For this set, all the limit points is contained in here. So now we are going to show the relationship between these two sets. So now we are going to see one small result. So I will put it like a theorem so that you can put the numbers. If E is any subset of the metric space M, then we have the relationship the set E always a subset of E. So now how to prove this? We know that to prove a set A is a subset of B, what we will be doing is we will take one general element from A, that is, let X belongs to A. Finally we will try to prove that this X belongs to B. If this happens, then every element of A belongs to B. So this implies that A is a subset of B. This is what we do to prove set A is a subset of B. So now we have to prove that the set E is contained inside its closure. So now what we are going to do is let us take one element in E. Clearly the sequence, you have to be very careful in putting the symbol E. I am going to take one element from the set E, and we are going to prove that this X belongs to its closure. So clearly the sequence, see the repeating sequence like this. See, I take this element, this X itself I am going to repeat it, and this is one sequence. Clearly this sequence converges to X. Clearly it is obvious that this sequence converges to X, and this is a sequence. More clearly I have to write like this. Clearly the sequence in E converges to X. Hence X is a limit point of the set E. That is the definition of limit point. So there exists a sequence which is converges to that point, and that point belongs to what? So X is the limit point of the set E. So X is the limit point means, as per the definition of the closure, this X must belong to the closure of the set E. Therefore, we took X belongs to E, finally we proved that X belongs to its closure. Therefore, always the given set is a subset of its closure. So it will be like this, always you can keep in mind. This is the set E and this is the closure. So all the limit points are here. So now the next important definition, that is a topic, that is closed set. If the given set and the closure are equal, then we say that the set is a closed set. That is, all the limit points will be inside the set E itself. If this happens, then that set will have this property. E will be equal to the closure. That is, all these points which is limit points which are outside this set E will be inside this. So what will happen? This E and E bar both will be same. So E and E bar will be same. So that is the next definition we are going to see. So but in general, a given set E will be a subset. This is true always. Always this property is true. Whether this closure is a subset of E, that is a question. If we prove this one, then the given set and the closure are equal, because this set relationship is always true. Just now we proved it. Okay. Now, so this is one result. Now we will see some examples in which the closure and the given set are not always equal. Already just now we told that always this given set will be a subset of its closure. Very rare cases there will be equal, then that set we call it as a closed set. That is, the limit points also is inside the given set. So closed set. Now we will see that some examples. One example in which the limit points is not inside the given set but outside. So E bar and the closure and the given set are not equal. Now, for example, some examples we are going to see. Let E denotes, suppose E denotes the open interval 0, 1, and the metric space under consideration is the real line with usual metric. So like this, the entire real line, this is a metric space under consideration, and in that we take one small subset, that is 0, 1, open set. All points in between in 0, 1 except 0, 1. This is our set E. Then 0 is the limit point of E. Here 0 is, yeah, we have to use the word A always, because there is not only one limit point, there are many limit points for the given set. So 0 is a limit point. 0 is a limit point of E. Because why it's a limit point? Limit point means you have to find one sequence in E that is converging to 0. Clearly, since, why it is a limit point? Since the sequence 1 by n equals to 1 to infinity, you can omit the first term 1 by 2, you can put 2 to infinity, because n equals to 1 means the first element is not belonging to the sequence, so you can starts from n equals to 2 to infinity. So what is this sequence? 1 by 2, 1 by 3, 1 by 4. 0 is a limit point of this sequence, this set E. Why? Because we found one sequence, say like this. Since the sequence converges to 0 clearly, but 0 is not in E. You can see clearly 0 is not in E. Therefore, clearly for this set the limit point is not inside the set E itself. For this set, therefore the closure will contain, sorry, we can write like this also. So here the given set E is definitely a subset of its closure, because at least one limit point we found out here that is not belonging to E. So this is one small example. On the other hand, this is the first example you can consider. The second example is a little bit change, we are going to take it. The set E, I am going to take the closed interval 0, 1. So what is this? Same thing. 0 is included and 1 is also included, and all points in between them is also included. In this set, all the points, all the limit points of this set is inside the set what? E. Here, all the limit points of E are inside E. So here for this set, this closure will be equals to E. Because if you have any holes like this, then then only that point does not, that limit point does not inside, this does not present inside the given, here 0 is a hole. Okay, here 0 is, you see this same sequence is here also, the same sequence, you can start from 1 to infinity. Here the sequence 1 by n, where n starts from 1 by n, this has a sequence converging to 0. So no limit of the sequences inside this set will be outside E. So this set is a closed set. That's why we call it as a closed interval. The name itself suggests it contains all its limit points. Now, this is a second example. Now, the main definition. What is a closed set? This is an important definition. Closed set. The subset E of a metric space M is said to be a closed subset of M if the given set is equals to its closure. So now in future, if you are going to prove a set is closed, so what you are going to do is always the given set is a subset of its closure. This is proved. This is always true. There is no need to concentrate on this. You have to show only that this closure is a subset of E. So what you have to do is you have to take one element from the closure and try to prove that that belongs to E. That alone, if you prove it, then this is automatically satisfied, and hence the given set is a closed set. So this is the technique we have to use it for proving a set is closed. Now the next theorem result. Let E be a subset of the metric space. Let E be a subset of the metric space M. Then the point x in M is a limit point of the set E if and only if every open ball, say B, with center at x and some radius, or about x contains at least one point of E. Contains at least one point of E. So this is a very important result. We will be using it in many of the theorems to come. So this is an if and only if. This condition is necessary as well as sufficient condition for x to be a limit point. So what it says is, suppose E is a subset and we say that x is a limit point of the set if and only if whatever open ball we take, every open ball about center x will contain minimum one point of E. Suppose this is the set E Suppose this is a metric space, and this is the space set E under consideration. If I say that this x is a, we say that x is a limit point of E. The definition is there. We are not going to use definition always. We are going to use this theorem. What is the theorem says is, if x is a limit point, what it says is, whatever open ball we consider, whatever, any open ball, the radius alone will change. Center is same. Radius is increases, so it will be like this. Suppose radius is small, it will be like this. Whatever open ball we take, no, we should not miss any open ball. Any open ball we take with center at x, but radius is varying, that will contain minimum one point of the set E. Minimum one point of the set E. If this happens, then the given point x is a limit point. So if x is a limit point, then this property will be satisfied. If this property is satisfied for a point x, then it is a limit point. So this is the necessary and sufficient part we are going to put. So now, necessary part. So the necessary part is, we will assume that the given point x is a limit point, and we will prove that any open ball we construct with center at A, radius is maybe changing, then every open ball about x will contain at least one point of the given set E. The necessary part we are going to prove. So forward implication. So what we are going to assume is, suppose x element of M is a limit point of the given set E. So what we are going to prove is, we are going to consider generally an open ball, say B, whose center is x and radius is changing. Maybe radius is an arbitrary element. So we are going to show that this open ball will contain at least one point of E. So we will come to that later. Now we are going to use the definition of limit point. X is a limit point of E. So what is the definition says? Hence, there exists a there exists a sequence. Hence, there exists a sequence, say xn, sequence of points of E converging to x. Now I am taking an arbitrary open ball. Radius is an arbitrary radius, not a fixed one, or is arbitrary. So if we show that this open ball contains at least one point of E, then any open ball will contain any point of E, or at least one point of E. So that's why. Now we are going to take one open ball, generally an open ball. If B of x, center is x and radius is an arbitrary real number greater than 0, hence if B is any open ball about x, any open ball about x, so I am generalizing it, then this B of x r contains xn for any n such that xn comma x is less than r. So this one we are going to use the definition of say I will just put a bracket here. This is just for explanation. So what is the limit of a sequence? Limit of a sequence. So suppose this sequence xn approaches x. So what is the definition says? For given epsilon greater than 0, there exists a n in I, a positive integer n in I, such that How is that? Whenever my n is greater than or equal to Kaplan, because we are dealing with metric space, so we have to be very careful using the symbol. The distance between xn and x will be less than epsilon. So here in this definition, in place of epsilon, we are going to use r. That's all. R is a real number that is greater than 0, and so here that's what we are going to link this one and the open ball definition. So what is the open ball definition says? So what is the meaning of B of x colon r? Set of all elements y such that the distance between x and y must be less than. This is the meaning of the definition of open ball. So a sequence converges means, so this one how can we link with open ball? This is nothing but all xn will be an element of the open ball whose center is at x and radius is epsilon. That epsilon is r. See, this is what is written like this in terms of open ball. Both are same. Both are same. Instead of distance between xn and x is less than epsilon, we are writing it xn belongs to the open ball, its center at x and radius is r. And this is true whenever my n crosses Kaplan. So that is what is written. If x is any open ball, since this xn is a sequence converging to x, this open ball contains xn for any n greater than or equals to Kaplan. We can put the word here. Contain xn for whenever n is greater than or equal to Kaplan. Then here I can change it. Then okay. We can change the words. It's our wish. We can write it in our own words. So here, if this is an any open ball about x, then I can erase this. Simply I can write. Then for a given epsilon, that is r, then there exists an n in I such that I am using the definition of limit of a sequence such that xn is an element of the open ball for every n greater than or equal to Kaplan. This is what we can write. Simply we can write like this. So there definitely exists n. So we used here by using the definition of limit of a sequence in terms of open balls. So we use this concept. So here what we proved it, not only one element, many elements of this, all this sequence belonging to it, E. So not only one element, many element belonging to this open ball, but this open ball is a general open ball, R is an orbital element. So any open ball with center x will contain at least one point of E. So that is what we proved it. And therefore any open ball about the x contains at least one point of E, hence the necessary point. Now we are going to prove the sufficient part. Sufficient part we are going to prove. That is, we are going to assume that any open ball about x contains at least one point of E. Then we will prove that that point is the limit point. Now let us consider a point x in M, and suppose we assume that suppose every open ball B with center at x and radius is r. Every open ball means we are going to take r as an arbitrary radius. This can change. This r, this suppose this every open ball contains at least one point of the set E. Then for any n in I, the open ball, now this is a general statement. So any open ball but center must be x. Any open ball center must be x, radius can change, this can change, will contain at least one element of E. So now I am going to change the radius and create many open balls. So then for any n in I, the open ball, say, see, this is the open ball we are creating, say x, center is x, but the radius is 1 by n, contains a point, minimum one point it contains. Suppose this open ball contains a point, say xn, to denote that this xn belongs to this open ball. x2 will be an element of the open ball with the radius will be 1 by 2. x3 will be an element of an open ball same like this, but radius is 1 by 3. So to link this element and that radius, we are writing like this. So suppose this open ball contains at least one element, say xn of what? Means at least one point xn in E. Now the sequence, now like this many open ball we create one element we take from these sequences. Suppose the first open ball B of x colon semicolon 1. From this we are taking the first element x1. From this open ball center x radius 1 by 2, we take one element, say x2. Next another open ball, the radius is reducing. In this I take one element x3. Like this we collect all these elements, that is a sequence. So the sequence, say xn, is definitely a sequence of points in E. Definitely it is a sequence of points in E. Converges to x. How we tell that it is converges to x? Because you see, keep on the radius is reducing. So now why it is converges to x? We are going to give the reason here. The sequence points converge to x. Since in general the distance between x and xn is less than what? 1 by n. Because if this x1 has to be inside this open ball, so what is the relationship it should satisfy? The distance between the center and x1 must be what? Less than 1. What is the condition? This should satisfy rho of x comma x2 must be less than 1 by 2. So if this element x3 should be inside this open ball, then it should be rho of x comma x3 must be less than 1 by 3. In general, if suppose there exists an open ball like this, from this we take one element xn. So what is the condition? The distance between x and xn must be less than 1 by n. So what happens when n tends to infinity? What happens to this ratio, this distance? It becomes very close to what? 0. So clearly the sequence converges to x. That is, I can find that n, capital N, such that after that n, this elements comes very close to this x. The sequence points comes very close to x. So from this we can clearly identify that if n tends to infinity, what happens? The distance between x and that elements, sequence elements, are becoming very close to x. Hence Since we found out a sequence in E converging to this x. Therefore, what you can tell about x? Hence, x is a limit point. X is a limit point of E. So that is what we proved in the sufficient part. Hence the sufficient part, and hence the theorem. This completes the theorem. Okay.